Hey, it's Papa. We've been talking about serpentinite, how it's formed and what it's made out of and what it does. And I'm going to tell you all about that. But before I can do that, I have to show you what happens at a mid-ocean ridge that's producing new ocean crust, because that's where a bunch of serpentinite is born. So here we go. Here is a picture of a mid-ocean ridge where rifting is going on and a new ocean is being created. You can find a mid-ocean ridge right in the middle of the Atlantic Ocean between North America and Europe. And of course, all this volcanic activity is happening on the ocean floor underwater. The main thing to remember here is that new ocean crust is being created and pushed out both to the left and to the right. Let's look at the components of this mid-ocean ridge. At the very bottom in the olive green color is the very hot plastic mantle that's made mostly of peridotite and dunite. These are the most abundant rocks on the planet. This is a photograph of dunite from the Lake Burton dunite area. It is chock full of magnesium and iron, and the minerals that the magnesium and iron make in peridotite and dunite are olivine, which is a greenish kind of mineral that shows up more in dunite, and pyroxene, which is a super iron-rich mineral that's black. Above the olive green mantle layer is a layer of what they call layered peridotite, and that just means where peridotite has melted in the bottom of the magma chamber and then just forms these light and dark layers. Looks like a sedimentary rock. Next up above the peridotite is a layer of gabbro, and now we're really getting into the rocks that produce ocean crust. Gabbro is a mafic rock that contains mostly the minerals augite and calcium feldspar. You can see from this example that it has pretty large crystal sizes. That's because it forms way deep underground and never erupts to the surface. And so as it cools slowly, the crystals have time to grow. If gabbro does erupt on the surface, it becomes basalt lava. Exact same mineral content. Are you getting glassy-eyed yet from all this? Hang in there, we're almost done with this description of the mid-ocean ridge process. Next up, we have the actual eruption of this gabbro magma into basalt lava. And the basalt lava makes these long vertical dikes. And as the ocean grows on either side, a new dike is produced, and each dike feeds from a big blob of gabbro magma at its base. Here's what those vertical basalt dikes look like from the side. This photograph from Google actually comes from the Devil's Postpile National Monument, I think, which is in California. So this represents basalt lava that was erupted on land, but the exact same thing is going on the ocean bottom. If you look at those vertical basalt dikes from the top, they look like a man-made walkway. Each dike has 6 or 8 flat sides to it that make it really look man-made. This is a Google image taken from the top of the Devil's Postpile. Now when this basalt lava comes up out of the ocean floor and hits the cold ocean water, it turns into these pillow shapes. It's called pillow lava because it cools so fast. Here's what the pillow lava actually looks like in real life. This is a Google image, and I think this is from either Hawaii or California. So you're probably wondering, where the heck does serpentinite come in with all this? Well, ocean water at the mid-ocean ridge seeps down into the mid-ocean ridge crevice through cracks and faults. It makes its way all the way down to the bottom of the magma chamber and comes in contact with the peridotite/dunite of the mantle. The water is super hot and it reacts chemically with the peridotite and dunite and to form You guessed it, serpentinite. And that serpentinite comes up into the ocean bottom, mixed in with the pillow basalts. The serpentinite travels with the ocean bottom all the way across the face of the planet till it hits a continent and subduction occurs. And in the next video, I'll tell you the role that serpentinite plays in relation to subduction. Pop out.